In this video, we're going to talk about correlation. You can see in this particular book, it's section 7.3 and then carry into section 7.4. And we had talked about the idea of correlation a little bit in another video. And basically, we were comparing it to the XY coordinate axes. And so I'm going to move this out of the way for a minute and just draw a line over here. Okay, I'm going to start. And again, I'm going to draw a line. So I figured out how to get a straight line with this ruler function. And I've got to kind of jump back and forth with my mouse and writing pen. So it takes a little longer, but it's a lot better. Okay. Okay, we have this axis, and we're going to move this thing over here for a minute. And we were looking at the Cartesian coordinate plane, and we said, okay, that's the x-axis, that's this one here, horizontal, and the y. Okay, that's the vertical component. And x stood for one variable, and y stood for another variable. And then we talked about ordered pairs, and we said we could plot those ordered pairs of numbers on this coordinate plane. And for example, let's say that we have one here, point, and then I'm going to bring this back over and just turn it a little bit and put another point up here. Okay, and then these two points then represented an ordered pair of numbers, and the ordered pair of numbers would, let's say that's 5, 6. And again, I'm just making those up. Okay. So the 5 was, I'd start at the origin and then go over 5 and then I'd go up 6. So it was vertical distance away from the origin, positive to the right, negative would have been to the left. And then once we come over to our spot, our 5 units here, then the second number tells us how far to go up and down. And that's our vertical component, or in this case positive, which means go up that way off the x-axis. So we plot that point there. Then we have another one up here. Again, we're going to call 6, 10. And again, it's kind of a rough estimate, but so I can draw those. And then if I had a bunch of points and they were all from a what we call a pure linear relationship, the points would all be along this line here. So I'm going to draw a line. And it's going to come down and just go down that way and keep going up that way. Okay. All right. So we have our line there. All right. So much better than the last video. Now, then we just show this arrow keeps going off to infinity that way and down that way infinitely. in that direction. So this line, yeah, there's these 2 points on the line, but there's also millions and millions of other points on that line also all along here, right? In math, we say an infinite number of lines, right? Just lots and lots and lots and lots and lots of ordered pairs of numbers or points, right, that are on this line. So this was defined as a linear relationship, right? It's a linear relationship between x and y. So linear meaning that the rate of change or the slope of this line is consistent. We had our slope formula. We had that m equal to y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. So we could take these ordered pairs, and again, it didn't matter which one was 0.1 or 0.2. If that was 0.2, we could take 5 comma 6 and put 5 and 6 in here and find the slope of the line, and then we could take 6 comma 10 and put 6 and 10 and find the slope, and so on. And again, I'm using this idea though to lead into correlation, because in a way it wouldn't be wrong to say that there is a correlation between the x and the y variables here. Okay, so there would be a relationship, and well, yeah, there is a relationship. We already said that there's a linear relationship because all the points in the solution set of the equation that defines this, they all form this nice line type function or linear. So that's where the linear idea comes from. Solution set is a line. The set is a bunch of points or a bunch of ordered pairs, an infinite number. Okay. All right. So now in correlation, in statistics, it's the same idea. And I'm going to turn this thing and draw another graph over here. And again, use this ruler so I can get my line straight. And I'm going to draw another graph. And we'll turn this thing. All right, so draw our x-axis and our horizontal axis. So we're going to come along here and go out, and there we got another axis there. So I'm just going to pull this out of here. And then, so when you talk about linear relationships in algebra, right? So this is like algebra. That's what you learned there, right? Over here, and you talk about linear relationships, we're going to call this statistics, right? And compare the two. Well, this is still, we consider the x-axis, right? There's our input. You could call that the y-axis or our output. And we could say that this is a place we could draw a relationship between these two variables, right? So remember that we were graphing like we did a histogram. A histogram, we talked about how it was a set of data values, and it referred to like one variable. And then this talked about two. And when you have two different things, you could compare them. We talked about different things like math score and your English score on two different exams, and then we could plot all those points, right? And the thing about statistics is that it's less, in a sense, theoretical and more realistic in what actually would happen. Because if we come over here, we could have said, okay, this was some group of math scores. This was like the relationship between math scores and or ability and English, and we wanted to say like, okay, yeah, it's typically linear, right? And then we could talk about that. Well, it's a line, and we could talk about the slope of the line and so on. But in statistics, in reality, if you were comparing people's math scores and English scores, and you plotted the points, it would look more like this. The points do not fall in a straight line. We can pretty much guarantee that. I can guarantee you that if you took a bunch of students and you looked at their math and English scores, they wouldn't fall all in the points wouldn't fall in a straight line. Okay. Now, so how can we talk about a linear relationship over here when there's not going to be a line? Well, what we do though is we say in statistics is how close do they follow this linear pattern? So when we talk about correlation, we're talking about, in this particular class, linear correlation. There's lots of different types, linear and nonlinear. There's quadratic and cubic and exponential and logarithmic regressions where they try to model points to lots of different types of statistical lines or models, okay? But we want to learn just about linear models in this particular class. So when we talk about correlation, we're talking about linear correlation. So the first question is there a correlation between these two variables? Well, yes, always. There's always a correlation between two quantitative variables. Now, what we need to do is describe that correlation. And what we want to do is try to describe it in terms of a linear or a line. Okay, and that's it. So what we're going to say is that, these kind of look like a line. They're kind of going up that way, and they're scattered about, but they're not like all over the place and up and it does seem to have a pattern to it. So we need to be able to talk about a couple different things with linear correlation and how we would then talk about the relationship between math ability and English ability. So this is over here a little more theoretical, not quite as useful, but we can use this idea. We're going to come back to this a little bit later and see that, hey, we're going to borrow this from algebra. We're going to borrow the slope and the equation of a line and look at that line. It's very important, but not right now. Let's talk about this, and I'm going to go back into the book here for a minute if I can find it. What did I do with it? There it is. Okay. So this is your the ebook, and it says here that a correlation exists between two variables when hires of one consistently go with hires of another, or when now, not that I am disagreeing with the authors here on this definition, but it's really could be better. Uh, a correlation always exists, okay? If you have two quantitative variables, we can generate what we call a correlation coefficient, okay? So a correlation always exists. I think what they forgot to do in here is talk about a good linear correlation exists between two variables when a higher value of one consistently go with higher values of another, or when higher values of one consistently go with low. That really is describing a decent linear. So try to remember that. And so how do we show, visually, like we had a histogram, which showed us a distribution, and it maybe showed us it was like normally distributed data or had some kind of outliers or had bimodal tendencies or something. But when we got two variables, two quantitative variables here, we use a scatter plot, right? So we're going to look and go to the next page here. And the scatter plot's a graph in which each point represents the value of two variables. So the ordered pair that we talked about. So every point here relates to an ordered pair. So for example, this one here, the first number would be 2. We start here and we go to the right and it's at 2 and we go straight up and it looks like it is about 11,000. Okay. So this point would be 2, 11,000. The weight, the carat weight would be 2 and it would cost about $11,000. That's a lot of money, right? All right, so we're going to see things like this, not straight lines right now with correlation. Here's another correlation between color and price. And it says, let's think about this. We want to look at the scatter plot. What is this really saying? Are these points, first of all, kind of looking like a line almost? Well, no, actually, they're kind of all over the place. They don't look like a line. We could come up with any kind of linear pattern. So can we run a linear correlation on this, and use a formula to see how strong are we? Yeah, we could. So we can always, even though it doesn't look like much is there, that helps us initially say that, color, as color increases, price really doesn't seem to be affected that much because this, this is 8 or 10,000 here for 2. Well, for 6 on the color chart, it's about 8,000, 9 around, and if you go up to 8, it's about 8 or 10,000. So there's not much there. So let's go ahead and go to the next page. And let's look at how would we describe these types of correlations. All right, there's two things that we discussed with linear correlations, okay? Now, first of all, the symbol is R. So you see R, this lowercase letter R is the sample symbol for correlation, right? So R equal 0.3. Now these numbers 0.7, 1, negative 0.3. If you'll notice, they're all between -1 and 1. Okay, so we have, and I'll be kind of jumping back and forth on this. So I'm going to clear canvas. And I'm going to put this thing away, and we're going to write up here our correlation coefficient. All right, so correlation coefficient R sample. Right? This is for the sample symbol, but R is going to be between 1 and -1. So they had some numbers in there like R equal to 0.3 and R equal 0.7 and R equal 1, R equal -0.3, R equal -0.7, and R equal to 0. So there's all these different ones you see there. They're in this range here. All right, and now let's look at the difference of them visually. All right, so all right, there we go. So types of correlation. Well, two things. The direction. they're positive, we consider them positive or negative. And then we have a special case of like slope when there's no slope or no correlation, because we could have zero slope. Right, we had a zero slope. We could have zero correlation too. And so we want positive or negative, and then the number, the strength. So we want the direction, right, and the magnitude of the correlation. So let's look at this. So two things we could talk about. Well, with algebra, when we had a line going, when we were going from left to right, we talked about slope. We said if the line went up, like these points are kind of going up as we go from left to right. Okay, that's positive slope. In this case, this is a positive correlation also. This is going up, okay? Positive. This is going up, positive. These are going down slightly, but they're still going down, negative. This are going down, negative, negative. Here's our special case. They look like a big circle. They're like in a big scattered about circular pattern. That's zero. That's what zero means for a linear correlation. Now you could look at this too, and you could say, well, that looks like a line. No, that's not really, it's a curve, right? It's definitely not, if we drew a straight line, this would go out this way. So this has no linear correlation either, okay? This would be like zero also. Zero in its form of a line, right? Looks like an upside down parabola more, right? Okay, so direction, pretty straightforward, right? It's going up or down, positive or negative. Then we look at the magnitude. Let's look over here first. These are right in a straight line, just like in algebra, right? Well, if they are in a straight line and they just look like a big straight line like in algebra, that's r equal to 1. That's the highest, strongest positive correlation. This one is scattered a little bit, 0.7, so close to 1. Here's scattered a lot, 0.3, not close to 1, right? So here's negative 0.3. So you could have a positive 0.3 or a negative 0.3. They're scattered about the same. They're the same strength. They both have the same strength of relationship between the variables. The only thing difference between these two is the sign. This is a positive 0.3 and a negative 0.3. So students kind of get that mixed up. They think negative is weaker than positive, but that's not true. Here's a 0.7. Here's a negative 0.7. Both have the exact same strength of relationship. One's just positive 0.7 and one's negative 0.7. Here's a positive one and a negative one. They both have the same strength of relationship. Perfect positive, perfect negative, right? Here, right, no real relationship between the two variables, no linear relationship. Same with this right here. So, all right, let's go back to this for one more thing. Now, what does that mean? Positive. Well, as x increases, y increases, right? So when we had positive slope, same thing, means the same thing. Positive correlation and positive slope in a linear function means the same. As x increases, y's tendency to increase. So there's the one difference between talking about slope and correlation, okay? See, here's a straight line. So as x increases, y is always increasing, always. The difference here is that as x increases, y does not always increase. For example, here's a point right here. When I go to the right, it comes down. So it's decreasing. From this point to this point, my correlation isn't, the line's going down between those two, right? But in general, for the most part, as x increases, y is increasing, right? Now in this one, we can find lots of cases where as x increases, y is decreasing, right? But overall, as X increases, Y has a slight tendency to increase. Okay, so I want to make sure we understand all those things. So there's a lot there in it. Now, this says measuring the strength. Well, we need a formula, and we're going to actually use our calculator. So we're not going to do this in this video right now, but we are going to uh, plug some numbers into the calculator and come up with some values. So let's talk about the properties. Well, we know that R is between -1 and 1. If there's no correlation, that's R is 0. All right. If it's positive, as one increases, the other one has a tendency to increase. If it's negative, as one increases, the other has a tendency to decrease. They move in opposite directions in a negative correlation. Okay. Now let's take a look at this. These are just some examples. This is kind of pretty linear, right? It's got a little curve to it, but that would be a strong negative correlation, right? This might be a negative 0.9. It's not a 1, but it's pretty close. So as the number of farms increase in millions, the mean size, acres, increase. Okay. Let's look at this. Kind of linear. It's positive. Strong positive. Same day forecast. Actual temperature. So they predicted 30. They got like 35, right? Same day forecast. So it looks like there's a pretty good relationship between same day forecast and the actual temperatures. So they do a pretty good job for the most part, right? That's what that's telling us. 3-day forecast actual temperatures. Well, you'll notice it's not quite as linear here, but it's pretty good. So they're not quite as accurate as predicting the actual temperatures 3 days in advance, right? We can see that this scatter plot's a little better, right? A little stronger. This might be a positive 0.7. All right, here's our formula. Here's our formula. And that's going to look at a lot of work there, right? Correlation, covariances, and then we had the standard deviations and n-1 and stuff. So this formula does take a lot of work. We're not going to do them by hand. We're going to put them into the calculator. And here it kind of shows you an example, scatter plots and correlation. And this talks about StatDisk, which is something that you do have access to. You have free access to this program, StatDisk. So if you want to play around with that, you can. But the TI 8183 or 8384 here, we're going to show that. And I'm going to just skip this here. You notice there's another alternative form of that equation. So that's, right, kind of scary there, right? That's a lot of work. But before I do that, I want to make sure I get through a few things in 7.4. And we're just going to, let's see, does that, we went one too many pages. There we go. Okay, so 7.4 in this book talks about interpreting correlations, and we actually have been doing that. So I'm going to kind of quickly move through this. And the one thing that they focus on here at first is they say outliers do affect correlation coefficients. And we talked about outliers when we were calculating measures of central tendency. Remember when we calculated the mean, if there was an outlier, the mean was kind of pulled away from the middle of the distribution, and we thought maybe the median would actually be closer to the middle than the mean when outliers were present. And this can kind of mess you up. If you look at this correlation between these 9 points just right here, you'd say, oh, it's a correlation of 0. But if you throw this 1 point up there, this 1 point, it changes your correlation to, it says right here, 0.88. which is really a big difference. So outliers can dramatically change or affect your correlation, right? So we need to remember that. And if we look at this, look how tight these points are. So ignoring this one and this one. So if we just looked at these points, we would say, wow, that's like a 0.9, 0.95 positive correlation. Very strong cycling per day in hours and calories burned per day. We would say that's incredibly strong relationship. But we look here and we think, well, maybe these people weren't pedaling very hard, or they weren't going up a hill, or they're going downhill a lot and they weren't burning so much. This guy here, he cycled a little bit and burned a lot. Maybe he's in a different gear, maybe steeper hills. So we'd have to kind of look at this and see, why are these two so different than all the other ones, right? So there's lots of things to think about with correlation. It can help us understand a set of pairs of data values. And we want to make sure we look at, too, we see things maybe like this, and we say, oh, weekly hours of TV and grade point average. Now, I really don't think that if we increase our TV watch and our grade point average is going to go up like for this. There may be a reason, why are these guys, well, maybe the TV that they're watching has to deal with the course that they're taking, and they're watching CBS or CNN, and they're talking about politics or something, and now the tests are on some things on TV. So that might, and then this group right here, see, as you increase your hours of TV, normally you would think your grade point average is going to go down. So we might be mixing up two different types of data. And so we would want to really have to look into that after we saw this. So scatter plots, again, they're exploratory data analysis techniques. They help us initially start to look at what's going on. Now we still need numbers, right? We need some numbers to deal with, just like with descriptive statistics. We had graphs and charts and all that to get us going. But so you see here, if we split the two groups, we do have one that's going up, right? That's group one. And then group two, we split these guys and we said, wow, that's kind of different. So here's another example where car weight in pounds and car price, and you see down here, weight and price are all, they're roughly about the same, because all the small cars are probably the cheap ones. So you don't get a lot of variability in either direction. It'd be hard to come up with any kind of correlation, even though there's probably a pretty strong relationship between car weight and car price when you're talking about lighter, inexpensive cars. But then way up here, you'll see that these are scattered a lot more. So weight may not influence price as much when we're talking about heavier, higher priced cars, right? And we have to, again, look in, why is that? Well, higher priced cars typically have probably other things in them that jack the price up, leather. They could be fancy cars, um, and different things, right, that could affect the price other than the weight. Now, here's just a couple things they throw in there. Uh, Correlation does not imply causality. So it's one of the biggest mistakes people make. They say, oh, these two variables are correlated. That means one causes the other one to happen. And that's absolutely not true. Correlation was never meant to identify causation. Okay, never. Can it give us some ideas or indications of where to look and what might be happening? Yes. It's a good statistic. We just have to make sure we don't misinterpret it. It said both correlation variables might be directly influenced by some common underlying case. So that's like a third variable. Maybe there's some extraneous variable that we're not studying, but actually it is involved in, like we talked about, the price of the car and the weight. And we're saying, well, you know, there's a correlation here. Looks like, what's the issue there? Why can we talk about car weight and car price? Well, the reality of it is, again, these more expensive cars, they're cars like, maybe in Lexus or Infiniti or Mercedes or something. These might be just higher priced because they're of a certain brand. So brand would be considered an extraneous variable affecting the price of the car way more than how much the car weighs. So we got to be careful and realize that very rarely do two variables operate in a vacuum and nothing else influences the relationship. And it says that one variable may cause the other, but it takes a lot of work to try to really figure that out. So we're going to just go past that. And this study, they talk about a study, and we'll get into that more um, in the next chapter. But that kind of finishes up 7.3 and 7.4. And in this video, I want to stop there because the computations, using the calculator and all that, it's going to be more appropriate when we get into chapter 8, and that's going to be on the next video. So continue to work on your homework problems and whatever, if you're doing the math lab, right, my stat lab, and we're kind of through chapter 7 in this book, and I'm going to move on and keep looking at the schedule, right? So we have this week, next week, and then it's going to be a little bit before we get to that next exam. And again, make sure you read the announcements in Canvas as always. If you have questions, let me know. Shoot me an email.